So as Charlie said, this work really grew out of the year I spent at the State Department, where I worked with the diplomats who negotiate climate agreements for the United States, and I also served as the science advisor for Todd Stern. And those two things in that year in Washington really changed my perspective on climate change. When I came in, I was a natural scientist who'd thought about these issues for 20 years, but never really had much of an opening into the policy. When I left after that year, I had at least some grasp on the challenges that policy poses to progress on climate change. And I've tried to integrate those two backgrounds in the story I'm going to tell you today. So first I want to just take a minute to tell you about what I have done for most of my career. Most of my career has been spent reconstructing climate change in the past, specifically on geological timescales. This is one example of how we do this. This is a cruise we went on in 2009 off the Galapagos Islands. And this is actually how we take cores from the bottom of the ocean. Basically, you punch a PVC pipe into the ocean floor. You get a column of sediment, and in that sediment are various kinds of signals that tell you about climate history. In this case, we were studying the history of the climate of the tropics, and we were specifically after the shells of these planktonic organisms that float around the ocean and basically record in their chemical composition aspects of ocean history. Now, there's a specific aspect they record that I was one of the folks who made a key discovery in that area, and that is we found out that the magnesium content of these shells records the temperature of past ocean waters. And that discovery, which was about a decade ago, enabled us to make a series of reconstructions, especially in the tropics, about climate history that got me quite interested in the whole question of temperature evolution, both in the past, the present, and the future. And I'm not going to talk about the past today, it's a different subject, but that's really what led me into the work I want to, well, that led me to the State Department, I should say, first. So as Charlie said, in 2010, 2011, I was able to be a Jefferson Science Fellow at the State Department. This is the only time I met the secretary, frankly. It was just for a photo op. But I was very impressed by her. But anyway, 12 of us came to the State Department and worked in various bureaus in state. We had to get top secret clearance. It was a very, very different experience than being a professor at UCSB. For one, I had to buy nicer clothes. But again, the perspective I got there on this problem of climate change, I think, was invaluable. Okay, so let me start right in with the question that I want to address today. So Todd Stern is the special envoy on climate change at the State Department and for this administration. He was appointed by Barack Obama, President Obama, and Secretary Clinton at the beginning of the president's term. And a special envoy basically has a role that supersedes the normal diplomats and bureaucrats that work at the State Department. In a sense, they have a direct line to the president's thinking and can cut through some of the lower level negotiation issues that sometimes hold up progress. So, you know, Todd is a pretty formidable guy. He's a lawyer by training, extremely well-spoken, extremely well thought of, I think, in DC. And my interaction with him was often, frankly, by email, sometimes just on my BlackBerry. But in March of 2011, Todd sent me an email and he said, you know, this article had just appeared, and that's this one, right, that I've put on the PowerPoint slide. And I wonder if you could look into this question of whether a 1.5 degree or 2 degree temperature limit for global warming is feasible. And this was the article that prompted the question. This is Cristina Figueres, who is head of the UNFCCC, and she basically made this statement that we shouldn't just look at 2 degrees. It says here, I don't know if I can quite read it, 2 degrees is not enough. We should be thinking of 1.5 degrees. If we are not headed to 1.5 degrees, we are in big, big trouble. Well, that statement got some hackles up in the State Department because the US negotiating team and the president had spent a lot of time specifically negotiating this 2-degree limit as part of the Copenhagen Accord, which was basically December 2009, and then in Cancun was basically agreed to. And so when Ms. Figueres basically came out and said, well, maybe we should think about 1.5 degrees, the reaction was not so positive. But the scientific question of whether we can do either of these targets is a really, really interesting one. And the way Todd posed the question to me was, first of all, can we do it? And second of all, is this the right limit? Why not 3 degrees? Why not 4 degrees? What's the right number? So I spent about a month working on this. Typically the way things work in the US government is it's a fast turnaround. Typically you get a request in the afternoon and they want the talking points the next morning. In this case, I was given enough time to do a good job, and it was probably the most interesting thing I did there. And so this talk is an outgrowth of that work. Okay, so to answer the question, the first thing you need to do is look at the actual place where the 2-degree limit comes from. Well, this is the actual draft decision from December 2009 of the Framework Convention on Climate Change, known as the UNFCCC. And you can see that this text, which was, by the way, partly written by the president, or at least with the help of the president, it states very clearly that we shall recognizing the scientific view that the increase in global temperature should be below 2 degrees Celsius. Now, it's a very interesting question as to where that 2-degree number comes from. And it's a little bit beyond the scope of the talk, but it actually goes back to some work or some ideas Bill Nordhaus of Yale University advanced in the 70s. And then it kind of generally became adopted by the German government in the 90s. And so that's really where the 2-degree limit comes from. I'll tell you more about whether it's the right number. That'll be the first part of the talk. But that's what ended up in the Copenhagen Accord. There was also this 12th item in the Accord, which says that as the science advances, we should reconsider whether 2 degrees is the right limit. Perhaps we should consider 1.5 degrees. So Ms. Figueres, in her statement, was actually justified, I guess, by that point number 12. Okay, so as I said, there are 2 parts to this question. I want to address both of them. I'll start with the first, which is why 2 degrees Celsius? Is this the right choice? And then the second part of my talk will look at the question of feasibility. Okay, so there are different ways to frame this question of the 2-degree temperature rise. An obvious thing to think about is the impacts of global temperature rise. How will the Earth change if temperatures rise by 2 degrees? And how will that affect different systems on the Earth? A second way to look at it is the question of tipping points. Tipping points are recognized as parts of the Earth system that if they get beyond a certain threshold, they're going to move very rapidly to a different state. And that's probably the one I think is one of the strongest arguments for establishing a temperature limit, although I'm not convinced necessarily 2 degrees is the right number. A third way to look at this is the impacts on extreme events. Obviously, extreme events probably are the ones that have, well, I'd say along with tipping points, are the ones that probably would have the greatest human impact. We think about floods, hurricanes, storms, droughts. What other you might consider, obviously, if some of those extreme events would be known to accelerate above a certain temperature limit, that would be a good rationale for thinking about trying to limit warming to that temperature. And finally, one that I think hasn't been considered before, but I think is a very strong candidate, is the question of ocean acidification. So I'm going to go through these 4, and then I'll get to the question of feasibility in the second part of the talk. Now, this is a really famous chart that's become euphemistically to be known as the burning embers chart. It was featured in the 3rd assessment report of the IPCC. The IPCC is the Intergovernmental Panel on Climate Change. Roughly every 7 years, they release a comprehensive, very carefully authored report about all aspects of both physical, social, and economic issues related to climate change. I believe Charlie is a lead author on the IPCC report. And in that third assessment report, which I believe was 2001 or 2000, there was this famous chart that became to be known as the burning embers chart. And the idea behind it, charts have a lot of power, right? There's words, but then what typically happens with these, if you pick up these assessment reports, they're bigger than phone books used to be. And let's face it, most people don't read them. So what they do is they basically extract some of the text and some of the key figures into what are called summaries for policymakers. And those are the things that tend to have the biggest impact. Actually, one of my roles at the State Department was to work and approve the summary for policymakers associated with the Extreme Events Report, which was just released this year. This is one of those charts that ended up having an outsized impact. And the real reason is people thought of each of these columns as representing burning embers that got gradually hotter or worse for our planet or our society, either way you want to think about it, in association with temperature rise. And I don't know, for me it's a little hard to read from the side. Hopefully for you can see these numbers. But they go from a scale of 0, 1, 2, 3, 4, 5 degrees. And here's the part as of this time that had already been experienced, about a 0.6 of a degree warming. So I've placed this line just to show where a 2-degree warming would actually occur. Okay, so the divisions basically are, the first column represents risks to many. The second column represents, I'm sorry, I read that wrong, excuse me. Risks to unique and threatened systems. I'm going to read off this because it's going to be easier. Risks of extreme weather events. Distribution of impacts, aggregate impacts, and risks of large-scale discontinuities. These would be like tipping points. And you can see some examples of each of these 5 categories. For example, loss of unique and threatened systems, such as coral reefs, tropical glaciers. Increase in extreme events would be number 2. Number 3 would be some regions or countries face greater harm than others. 4 would be impacts distributed across the globe, such as economic impacts. And finally, these are the tipping points, which I'll have more discussion about. Now, when you look at this slide, if you just accept the graphics that whoever made the slide, and Steve Schneider at Stanford had, I think, a strong influence on this slide, place those red bars properly. I mean, if you didn't know much, you might just say, geez, I'm not even sure 2 degrees is going to be right, because maybe we should put this line somewhere down here, because we don't want to get into the red area on any of these 5 things. We don't want to lose coral reefs, for example. But of course, the judgment call about where to place the red is very much a subjective judgment. So what I wanted to do was look a little bit more deeply into this question of whether that 2-degree placement is the appropriate one. Now, a guy named Tim Linton, who's a British scientist, has, along with Hans Schnellhuber, who's a German physicist interested in this question, has done a lot of work looking at this question of tipping points. I can't tell, can folks actually read what's written on the slide? Okay, that makes it more challenging. So I'll try to read this out, but you can hopefully get the basic idea. So what this illustrates is tipping points that you could postulate might be responsive to specific global temperature rises. Some of these will probably be very familiar to you if you've seen Al Gore's An Inconvenient Truth, or if you followed any of the popular media on climate change. So here's the Greenland ice sheet. That's an obvious one that there's concern about. Here's the West Antarctic ice sheet. That's the more vulnerable part of Antarctica. Here are those tropical coral reefs I just made reference to. This is one that received a lot of attention about a decade ago, the Atlantic Thermal Haline Circulation. You might have seen the movie, oh, and I've dropped out of my memory. The Day After Tomorrow, thank you so much. You might have seen the movie The Day After Tomorrow that postulates that this could change overnight and we're all going to be covered in a wall of ice, or at least those of us who live in the Northeast. Not very likely, but there was this kind of paradigm that was quite popular about 10 years ago, that this could really rapidly shift, that it could be a tipping point. I would say that's something that's maybe less in vogue these days. So here are the ones that I picked out for Todd that I thought had the greatest likelihood to be sensitive to this specific question of a threshold temperature that could trigger a tipping point. So I put in that category, and again, these are my subjective judgments, partly on my reading of the literature, partly, and I would say in large part on 2.5 decades of work in the paleoclimate arena, where many of these, our understanding of many of these tipping points comes from, because many of them have quite long time scales that can only be evaluated through geological data. So the Greenland ice sheet is an obvious one. Amazon rainforest dieback, that's a particularly good one because we have some indications from 2 very large droughts that happened within the last decade that there could be a big impact in how much carbon is being taken up in the Amazon. And that gets into the question of carbon cycle feedbacks, which I'll touch on in the second half of the talk. West Antarctica, we put very much in a category with Greenland. Permafrost is another one there's been a lot of discussion on, whether you're discussing release of carbon or methane. That's again an example of a carbon cycle feedback. And tropical coral reefs, I think, is another one that really makes it harder not to be able to see it, but we'll do the best we can. Tropical coral reefs are something that there's pretty clear evidence right now are really suffering a degradation. Now, what's causing that degradation is a combination of rising sea surface temperatures, increases in ocean acidification, and also fishing pressures and other environmental degradation. So it's a little bit hard to separate out, but those are the ones I thought would be good candidates to think about in terms of threshold temperatures. So the next question would be, is 2 degrees the right number? I think it's really hard to say. I think something in the neighborhood of 1.5 to 4 degrees is probably the triggering point for most of these thresholds, but I had a really hard time nailing down which one would correspond exactly. Obviously, if this were an easy problem to solve, right, we would just say, hey, let's just keep it below 1.5 degrees so we don't have to worry about it. But that's not the framing of the problem, as you're going to see later on. Okay, so let's move to extreme events. Obviously, extreme events are probably where society is most aware of climate change. People pay attention when you have 100 days of 100-degree temperatures in Texas. People pay attention when you have droughts that wither crops, whether they're due to global warming or not. So that's something that obviously has to be looked at in terms of its sensitivity to global temperature rise. Now, the IPCC, fortunately, released an assessment report called the SREX, the Report on Extreme Events, this past year. And again, as I said, at the State Department, I was on the government review team for that. I worked with other distinguished scientists reviewing the text and sending in questions to the IPCC. And I also was at the plenary in Abu Dhabi, where we looked at and approved the summary for policymakers. And what I'd like to say to you is that this is a really good report. It's really well done. The IPCC has been criticized on some other grounds, but in this case, I think it's just really authoritative, it's conservative, it's careful, it's backed by the best science. So what I did is I just extracted some of the major points where you can see a distinct relationship between extreme events and temperature rise. So there will be a substantial increase in all of these things are preceded by the statement, as temperatures rise. There will be a substantial increase in warm temperature extremes. Okay, that's not a big surprise. Maybe we're having that today. It is late October. It's a bit toasty out there. The frequency of heavy precipitation over many areas of the globe will increase. Basically, warm air contains more water vapor. That, in turn, gives rise to heavier rainfall. And therefore, you can predict theoretically and also empirically that the frequency of heavy precipitation events will increase, and that would, one would think, lead to greater incidences of flooding. Average tropical cyclone maximum wind speed is likely to increase. It's not a very large increase, and actually, the frequency of events either stays the same or decreases, so I'm not sure that's a major one. The fourth point, droughts will intensify in some seasons and areas. Again, it's not real satisfying, but that's what the conclusion of the report was. One of the places was the Southwest United States, another place the Mediterranean. But in other places, it was much hard either to pull a signature out of the past or to make a prediction for the future. Mean sea level rise will continue to upward trends in extreme coastal high water. Sea level is rising 3 millimeters per year. So that makes sense. And finally, changes in heat waves glacial retreat and our permafrost degradation will affect high mountain phenomena. Okay, so those things again, like the tipping points, they sound like things we want to be aware of, but it's difficult to establish a cutoff temperature above which extreme events accelerate. Again, the question we'd like to know is, at what point do these things become intolerable in terms of our ability to adapt to those changes? And my reading of the literature, and particularly of the SREX report, is it's really hard to say what that discrete temperature limit is, other than to say for sure that as we go to warmer temperatures, we're going to have to adapt to a greater degree to such extreme events. Okay, the last category I'd like to touch on to the question of the temperature limit we'd like to aim for is one that's a little bit more satisfying, because we can really scientifically nail down what the number is. And again, I think it's really worth noting this one, because it's not one you hear you hear about ocean acidification, but you don't hear about it concatenated with the question of global temperature rise. Now, Mike Eby and his co-workers, particularly Dave Archer and Andy Weaver, put out a very nice paper in Journal of Climate a few years ago, just 2009, where what they did is they ran a model and basically looked at the linked question of ocean acidification and global temperature rise. And it's probably going to be a little hard to see the charts, but I'll just give you the basic message. What these show are the pH anomaly for particular injections of total carbon. And I'm going to get to this point about cumulative carbon just in the second half of the talk very shortly. But for now, I'm just going to say, if we release cumulatively a teraton of carbon, that's 1 trillion tons,